Okay. So I'm doing a presentation on the combustion of alkanes. So what are alkanes? Alkanes are chemical compounds that consist of carbon and hydrogen. These alkanes are built off carbon chains that fill the leftover bonding areas with hydrogens. So if you look at the picture here, we have our center carbon, and then it fills those three bonding area or four bonding areas here with extra hydrogens. But when you add another carbon in, and it's a carbon-carbon bond here, now we have three leftover bonds on each of these, and it's three hydrogens that join on each of these, so on and so forth. Um, we'll get a little more into this a little later on, but methane is CH4, that's one carbon chain. Ethane is C2H6, which is a uh, two carbon chain, and then propane C3H 8, which is three carbon chain, right? And you can see the Lewis dots here. Um, so combustion of alkanes are the reaction that expel large amounts of energy with small activation energies. Combustion reactions occur between an alkane, like methane, and oxygen, and that forms carbon dioxide and water. Um, You can see here 1 mole of methane, 2 moles of oxygen forms 1 mole of carbon dioxide and 2 moles of water. So if we look at these, we have different kinds of alkanes. There's there's a good amount here. Um, we have methane, ethane, propane. This is all just adding one more carbon to that chain. Um, and if you look at the structure over here, it gets very big very quickly. Um, so the type of alkanes are dependent on the amount of CH groups, right? How many carbons are in there. The shortest alkane is methane, and it's only holding one CH group, so therefore it's the lightest. And we'll talk about that in a couple of minutes, but the weight of these, atomic weight of these, really matters in the combustion. So if you look at these are all the alkanes, methane down to decane. Uh, Again, adding more carbons, so 10 carbons on here, one carbon up here. The higher the weight, okay, the more carbons and more hydrogens, the more energy expelled. So if you look at this delta H, enthalpy, heat content of a system here, the delta H increases by close to 660 on all these. Goes up, 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 all the way through. So every carbon you add, it is about 660 uh, kilojoules per mole. Um, you think about that, that's close to the amount that's broken when you get energy from breaking those carbon hydrogen bonds, and then a little bit is taken out because they have to form new bonds, which again we'll talk about in a little bit. Combustion alkanes are exothermic. They give off energy, so they're giving off 880 for methane, 1560 for ethane, so on and so forth. Um, it doesn't take a lot of energy to start these processes off. Like a lot of times, think about your car. This is an alkane. Actually, octane is your gas in your car. Um, all that is it started with a little ignition from the ignition wire in the engine. How is the energy expelled determined? How do we determine how much energy is expelled? How do we determine these values? Energy from these reactions are often represented by the term of enthalpy. That's what that H is. Enthalpy is the heat content of a reaction. Enthalpy is determined by the equation H equals E energy plus pressure times volume. So energy plus pressure times volume is the heat content, or the enthalpy. Enthalpy is equal to the energy plus the pressure multiplied by the volume. Same value can be found with the equation Q equals mc delta T. But the only thing different here is that you have to assume that the pressure is held constant in the system. So if the pressure changes, this Q will not be the same. If pressure is constant, Q will end up being the exact same as that H. So when we look at this stuff, this equation is very, very easy to use. We're going to take our M, that's our mass of our substance. We're going to multiply by the specific heat of the substance, and then multiply by the change in temperature. So if we look down here, we see a calorimeter. Calorimeter. We put our uh, alkane in here. Sorry, I said octane. We put alkane in here. And we have our ignition wires. We run a current through there. We ignite that alkane, and as long as we have oxygen enabling that combustion to happen, we can measure the change in temperature of this water. So at the beginning of this, before we light the alkane, this water should have a certain temperature. Let's say it's room temperature. After we light the alkane, this thermometer is going to rise. The heat from the inside in this alkane is going to warm this water here. The thermometer is going to rise, and we can determine how much the change in temperature is at that time. We can figure out a change in temperature T, multiply by a specific heat. That's a constant for everything. So there's a constant for the alkane that we're using. And then we know the mass of the alkane we put in there. So we can just multiply those all together. We'll get a Q, which is our heat expelled. And we'll see. In this case, this number should be negative because we're releasing energy. If we were taking in energy, this number will be positive. So alkanes are going to release energy, so it's going to be negative, which we saw here. We saw these negative numbers, right? It's releasing energy then. Is this process spontaneous? We will see that. So the spontaneity of a reaction can be determined by the Gibbs free energy equation. The equation G represents the Gibbs free energy. If the G is negative, then the reaction is spontaneous. Gibbs free energy of the combustion of methane is negative 818.5 kilojoules per mole, making the reaction extremely spontaneous. So after we start this reaction, after we have our first ignition, our first spark, this reaction will occur by itself. It will push itself through the reaction all the way through without any more energy going in. This value also determines whether products or reactants are favored in reversible reactions. There's two A's in that. So if we think about this, if this value is negative, which it is going to favor going to the product side. So if it's a reversible reaction and there's some sort of equilibrium in there, it is going to push it towards the negative, or sorry, push it towards the product side. So the reaction is going to be continuing forward for the most part. If it is a positive value, it is going to favor the reactant side, and it's not going to go very far in the reaction, right? It might work a little bit towards the products, but we're going to have a lot of reactants still left over versus the products. And we do find that this is spontaneous. Right? We look back here, negative 818.5. We said that a negative number means that it is a spontaneous reaction. So this G is negative. Gibbs free energy is based off of the enthalpy, right? These H's from the back side, change in enthalpy, the change in entropy, which is like the disorder of the reaction. I like to think of like entropy as disorder. So if you think of like a desk and you don't put any energy in to clean the desk and you go and you just keep setting stuff on there, over time that is going to become very chaotic. And if you don't put the energy in to take the take things off and organize them, then it's gonna keep becoming chaotic and chaotic and chaotic and chaotic. Uh, and that's the way it is in the solar system, or not, the universe, right? Think about the universe. If we don't put energy into something, it's gonna become more chaotic, more chaotic. So over time, the universe is becoming more disordered. It will always do that. It'll always trend in that direction. Um, so we know that entropy in the universe is always trending towards chaos. So back to the slide. Since we know the value of G is negative, we know that it is spontaneous. It's going to work right after that first ignition. It's going to work it, keep going, keep going, keep going towards the product side. It's not going to want to stick in the reactants, um, which makes sense. You need a little bit of energy to put in. You're going to get a lot of energy out, right? So we put a little bit of energy in. It's going to want to go until it's all out of energy to give for the most part. So we do say this is spontaneous. Some uses. One of the most useful processes of combustion is that the energy that is expelled from the reaction. So this energy that's held between carbon and carbon bonds and carbon hydrogen bonds are very, very high. And we put some energy in, break those, and that energy that is taken from those broken bonds, some of it's used to create new bonds between the carbon and the oxygen, and the hydrogen and the oxygen, and the carbon dioxide and water. But these bonds don't need near the amount of energy that the carbon-carbon bonds and the carbon-hydrogen bonds have. So we do see that there is leftover energy in both those cases, and we end up having to give off the excess energy as heat, light, so on and so forth. Um, that is why this is an exothermic reaction. It's not endothermic. If it was the other way around and it took energy in, then that'd be an endothermic reaction. Uh, some things we do see from this, since it does give off heat, gives off heat to change temperature. So this does change gas laws. This is how combustion engines work. The energy that's given off is heat, changes the temperature inside this cylinders. That pressure builds up in the cylinders and it moves the cylinders up and down, up and down, up and down, propelling your car. So the combustion of alkanes the combustion of alkanes give off large changes in temperature. These changes in temperature accompanied by changes in other variables due to their relationship. Charles and Gay-Lussac's laws describe the relationship between temperature and these other variables. So, like I said down here with Gay-Lussac, if I increase this temperature, my pressure is going to increase. So if I have a pressure of 1 atmosphere and a temperature of, let's say, 273 degrees Celsius, that's what standard pressure, standard temp, and I increase this to 500 degrees, 500 degrees, or let's make this easier myself, 546. Okay, so it's exactly double. If I increase this by double, then my pressure should increase by double, right? So if I have 1 atmosphere here and I increase this to 546, this is going to become 2 atmosphere. So they are or not indirectly, they are directly proportional to each other. Increasing temperature will increase your pressure. Same with Charles' law, they're also directly proportional. So if I increase temperature, my volume is going to increase. Think of a balloon. You heat up the gases inside that balloon. What's going to happen to the balloon? The balloon's going to expand, right? Then if you take that balloon and you put that balloon in some cold water, what's going to happen to the balloon? It's going to shrink up, right? Um, that's Charles' law. Directly proportional. If I increase temperature, volume's going to increase. If I increase volume, temperature's going to increase. Um, some examples of this: combustion of alkanes are used all the time. Alkanes are often used for various things. You think of propane. Propane's an alkane used in gas grills, used to cook food. Butane is often used in lighters as lighter fluid. Like I said earlier, octane is used as gasoline for cars. Um, then methane, natural gas heating. If you have gas heating in your house, methane is what is used. Use methane to heat your house. Okay. Here are my references. A bunch of references here. Uh, over pictures. There's some references on data where I got things, so on and so forth. That is all I have.